In this video, we are going to continue and finish our conversation about equilibrium constants for acid dissociation reactions. We'll then look at base dissociation reactions and a Kb value. So where we left off with our lecture last was we were using the equilibrium constant Ka here to find the pH of a solution. And so we were using two equations, the Ka expression, and we were also using this pH equation right here. And so this required us to find the concentration of H3O plus at equilibrium. And we did that using our ice table with our Ka expression, and then taking the H3O plus concentration and plugging it into our pH value. So now I want to look at what we do when we have a mixture of acids. And in general, I'm just going to give you kind of a rule of thumb to follow. If you have a mixture of acids and one of them happens to be a strong acid, and one of them is a weak acid, then the complete ionization of that strong acid is actually going to increase the amount of H3O plus in solution. And so if this weak acid is in equilibrium with H3O plus and its conjugate base, once this strong acid dissolves, we're going to see that equilibrium here shift left as we increase that concentration of H3O plus from our strong acid. And because of that, it means that we can calculate the pH of that solution just using the concentration of the strong acid, which really simplifies that problem. Now, if you're looking at a mixture of two weak acids, you generally need to only consider the stronger acid for the same reason. So if they have significantly different strengths, even though they're both weak, the stronger of those weak acids will have the same effect on the weaker acid's equilibrium as we saw up here with our strong acid and weak acid. So in general, you just need to calculate the pH for the stronger of your two acids that you have in solution. And there are definitely exceptions to this, where you'll have two weak acids so similar in strength that you really need to consider them both. But we're going to let that fall outside the scope of this course. So we track acid strength with pH we've talked about, and that's really tracking just the concentration of H3O plus in solution. And so that really tells you how dangerous the solution is. The Ka, remember, is really telling us where equilibrium lies in that acid dissociation reaction. And so Ka really tells us about acid strength. And much like we used pH to give a logarithmic scale for the concentration of H3O plus, we are going to use pKa to give a logarithmic scale for our Ka and our acid strength. And we're going to calculate it in the same way we calculated pH. The pKa is going to be equal to the negative log of the Ka. So really, anytime you're seeing that lowercase p, it's telling you to take the negative log of what follows. Algebraically, just a reminder that the way you solve for Ka in this expression is to take each side of the equation to the power of 10. And so when you do that, the log and the 10 will cancel out, and you'll have 10 to the negative pKa is equal to your Ka. So we see after we translate Kas into a logarithmic scale that the smaller the pKa is, the stronger the acid. Similar to our H3O plus concentration in pH, the bigger that concentration, the smaller the pH was. So our really strong acids, which we identified before as hydroiodic acid, hydrobromic, hydrochloric, sulfuric, they all have really small pKa's. In fact, they're negative. Um, Look, even our hydronium ion has a pKa that falls in the negative range. Oh, I've got one more. Nitric acid also is negative. And I guess this really shows us that hydronium ion is acting as a strong acid. So our weak acids are going to be pKa's that are larger, and we can see them here that they're actually positive numbers. But acetic acid, which is acid that you like a type of acid you would have in your household, like household vinegar, has a pKa of 4.76, which I think is a helpful context to have. Like this is a strength of acid that you work with regularly, possibly. So let's look at a quick example of calculating pKa. So if we want to track the pKa of hydrofluoric acid, and we know this is a weak acid, and I know that because my K is less than 1. Then the way we'll calculate this, and we can think of it as either versions of this equation, is we will take the negative log of the Ka. So in this case, it will be equal to the negative log of 3.5 times 10 to the negative fourth. Plugging that into my calculator, I get 3.46. So this is smaller than our acetic acid, but it's much larger than any of our strong acids. So that concludes our lecture on Ka. And now we're going to um, take a look at base ionization constants and base dissociation reactions. And we'll be able to apply the exact same skills we just developed to this section. It's just looking at a different reaction. So we have a base ionization constant, which is really just an equilibrium constant. And it's the equilibrium constant for a base dissociation reaction, which remember is our base plus water, and our water acts as an acid, and it will form a conjugate base of a hydroxide ion and then the conjugate acid of whatever our base was. And if we take the equilibrium expression of this, we'll have our products on the top right here, divided by the concentration of our base. Remember, we're ignoring water because it is in a different phase. It's liquid while everything else is aqueous in our reaction. So this is, again, developed just like any other equilibrium expression. And we're including a B right here just to say, hey, this is for a base dissociation reaction. We'll see that larger K is going to correspond to a stronger base, where a K larger than 1 would correspond to a strong base. And a K less than 1 would correspond to a weak base, where equilibrium favors our reactants. Here are some examples. Carbonate ion and aniline are both weak bases. The carbonate ion is this CO3 2 minus. Aniline is kind of this big thing right here. But the key part of it is that it is a nitrogen bonded to 2 hydrogens and a carbon. So there's that one lone pair here. I'll draw this all the way out. So this is going to be a lone pair on a nitrogen that is attached to a six-membered ring with resonance structures. However, that nitrogen isn't itself participating in the resonance structure, which provides less delocalization for this lone pair, which would be stronger, right? It's a more localized lone pair than if the nitrogen was actually embedded in at this position. And we can see a Kb here of that's really small, of 3.9 times 10 to the negative 10th, compared to carbonate ions, which have 2 oxygens with an extra electron on it. But again, these are also electrons that are delocalized throughout the entire molecule. But this one is much stronger at a factor of only 10 to the negative 4th. All right, so let's walk through an example calculating Kb for the reaction below. We're given equilibrium concentrations of the acid and the conjugate base. They're equal to 0.03 molar and 0.05 molar. Sorry, so the base is a concentration of 0.5. So this first step is to write out our dissociation reaction. Our base is NH3. We know it has to react with water to be a dissociation reaction, and it will act as an acid. Our acid will give a hydrogen to our base, so we'll have NH4 plus, and then we'll have OH minus for our conjugate acid and our conjugate base. So writing out our equilibrium constant expression for this, or our Kb, or base ionization expression, we'll have that NH4 plus on the top and our OH minus on the top as well. Our coefficients are 1, so I don't need to worry about exponents, and that'll all be divided by our base concentration. So I know that my conjugate acid and conjugate base, which is this ammonium and hydroxide ion, are both going to be a concentration of 0.003 molar. And my base is 0.5 molar. So I'm going to just plug this into my calculator. And I get 1.8 times 10 to the negative 5th. So that confirms that this is a weak base. Oh my, sorry. So just like we did with our acid dissociation constant, only we're working with a base instead. So the interesting thing is about Ka and Kb is that usually if you look this up, only Ka values are reported. And the reason for this is you can always find a Kb value if you know a Ka. So acid dissociation reaction and a base dissociation reaction are essentially kind of the opposites of one another in a way. And because we're having our water act as an acid and then also as a base in each of these. So if I take the acid dissociation reaction for an acid, and then I do a base dissociation for its conjugate base, and add these two together, I'll have a number of things that will actually cancel out on both sides. I'll have HA on both sides, and I'll have A minus. And so these will cancel out, and I'll be left with the net ionic equation that 2H2O will be on my reactant side, and hydronium ion and hydroxide will be on my products. And so really that's going to be, if I add these together, that's going to be the Kw expression that I know. And so from that, using the tools that we learned about manipulating K values, we can, since we added these two together, we can multiply Ka times Kb. And that's going to equal this third reaction that we know is Kw. So that allows us to say either that Ka times Kb equals Kw, or that our pKa plus our pKb equals that pKw. And pKw will always be 14 because Kw is always 1 times 10 to the negative 14. So we can convert in between these two. So if we want to know our Kb and we only know Ka, we know that our pKb will be equal to 14 minus our pKa. All right, in the next lecture, I'm going to start talking about the acidity and basicity of ions and salts.